Today we're going to start Chapter 2. Just a quick reminder that Chapter 1 and 2 are combined for a test. So our first test, I think, is, if you look at the gold sheet, scheduled for Friday, September 13th. And that will include Chapters 1 and 2. So Chapter 1, we focused on linear and absolute value functions. Those are graphs that turn out to be lines and V-shapes, and we're going to switch it over in Chapter 2 and put our focus on quadratic functions. The first set of notes today, Section 2.1, is all about vertex form of quadratic functions, which when we show you the vertex form, that should look fairly familiar from what we did in Chapter 1. So really quick review, what does it mean to be a quadratic function? Well, it's not linear, it's not absolute value, but basically your x has been squared. So that's going to look something like x squared. Now, all quadratic functions share a similar shape for their graph, and that is a parabola, so that's kind of like the U-shaped graph. If you're graphing linear functions, they should always be lines. If you're graphing absolute values, they should always be V-shaped, and if you're graphing something quadratic, it should always be in the shape of a U. Just really quickly over here, I'll do x and x squared table of values. We did this back in our notes 1.1. So if you want to flip back and look at notes 1.1, I'm going to put in -3, -2, -1, 0, 1, 2, 3, squeeze that in. If I square those numbers, I'm going to get 9, 4, 1, 0, 1, 4, 9. These are good points to know for your parent graph. What does your graph look like? So if we go, get 9, yep. If we go left 3, we go up 9. If we go left 2, we go up 4. -1, 1, 0, 0, 1, 1, 1, 4, and 3, 9. So I'll graph that one in blue. So this is your parent graph. Okay. But of course in Chapter 2, we're going to be graphing things that are transformations of our parent graph, and that's where vertex form comes in. So our vertex form looks like this: f of x equals a, not times the absolute value, I'm working in Chapter 1 right there, a times the quantity x minus h squared plus k. So hopefully you're looking at that and thinking, oh, a, h, and k, that seems familiar to me. We're going to identify transformations the same way, so we're going to be talking vertical stretches or shrinks, horizontal stretches and shrinks, moving right or left, shifting up or down, reflections, all of those things will be true. Now, this form, other than transformational form, is called the vertex form, and one of the reasons is because you can easily identify the vertex of the parabola. So over here in my parent graph, the vertex normally sits at the origin, 0, 0, and that's the turning point of the parabola. In vertex form, we can identify that as HK. And I'm going to put a little reminder here. H looks like the opposite. So we'll see that in our examples. Remember, when taking h out of a function, it's going to look like the opposite sign of what it appears. And then we're also in Chapter 2 going to introduce something called an axis of symmetry. So when we use this word axis, we really just mean the line of symmetry. Okay? And our parabolas are either going to open up or down. And so if we kind of look up here at our parent graph, what line does the parabola reflect over and onto itself? Well, that happens to be the y-axis there. And even if we reflect that parabola so that it opens down, it's still going to be the y-axis. So all of our axis of symmetries are going to be vertical lines. And so we're going to write those as vertical lines. Vertical lines are always x equals a number. In this case, it's always going to pass through the vertex, so that's going to be x equals h. So if you can identify your vertex, hk, you immediately know your axis of symmetry is x equals h, whatever the x-coordinate of your vertex is. And then something that we're going to add to our list of things we can do, or our skill set, is going to be identifying increasing and decreasing intervals. Now this will depend on the orientation of your parabola. So I'm going to, below this, I'm going to draw two images, a parabola that opens up and a parabola that opens down. So here's my parabola that opens up. Here's my parabola that opens down. They each have a vertex, which in one case happens to be a minimum. In the other case, it is a maximum. Through each vertex would be our vertical line that represents our axis of symmetry. So there's our AOS, and that's going to be x equals h, wherever this is on the coordinate plane. AOS, x equals h. And on one side of the axis of symmetry, the graph is increasing. On the other side, the graph is decreasing. Now, what order that happens just depends on whether you have a min or a max. So always read your graphs from left to right. So imagine you're starting over for this parabola that opens up on the left side of your graph. As you move to the right, you are decreasing. So we would say our decreasing interval would be for all x is less than h. And our increasing interval, once we hit that turning point, we change directions, will be all x is greater than h. Notice that I'm not including h in either of those intervals because that's the turning point, the vertex, so we don't know if it's increasing or decreasing right there. That's a very special point you study in calculus. Okay, but for right now, we'll just say to the left of h, we're decreasing, to the right of h, we're increasing, but we'll use inequalities, less than, greater than. And then looking at the parabola that opens down, that's going to flip-flop, right? If we're to the left of h, we are increasing. So our increasing interval is going to be x less than h, everything to the left. And when we turn, we're going to start decreasing. So we would say for all x's greater than h. Probably the most common mistake that students will make with increasing and decreasing intervals is rather than looking at the x-coordinate, where your axis of symmetry is, your h value, we might start getting fixated on the actual max or min value, so like the y or the k, but we're looking like left and right on our graph, where are we increasing and decreasing. So that line for a parabola is always split by the axis of symmetry. Okay, so we're going to take all of these things and we're going to be graphing and labeling things when we do our homework. So here's our first example. We're going to graph this function. You can write down the directions, or you can just kind of jot these things down as we do them with our graph. We're going to be labeling the vertex, the axis of symmetry, its domain and range, which is very similar to domain and range for an absolute value function, and then also our increasing and decreasing intervals. So our first function we're going to call g of x is -2 times the quantity x plus 3 squared plus 2. So I'm going to start with some of my labeling. Where is my vertex? If it would help you, you can always write that vertex form above. A times the quantity x minus h squared plus k. Remember, it's supposed to look like minus h, so if in the equation we see this plus 3, it's actually a -3 and then a +2. So there's our vertex. I also immediately know my axis of symmetry. That's going to be x equals -3. And I'll go ahead and graph those things and sort of get the rest of my parabola before I go into domain range increasing and decreasing. So I'm going to go left 3 and up 2, and there's going to be my vertex point. Okay. I'm going to sketch in my axis of symmetry because I can use the symmetry to get some additional points. Now, you could use a table of values to find more points, but we also know from chapter 1 that we can use our A value in front to kind of help us with what the shape of the graph is going to be. Since it's negative, we know our parabola is opening down, so instead of counting up, we're going to be counting down. And since the absolute value of A is 2, we have a vertical stretch by 2, which if I think about the parent function, I got that point at 0, 0. And then at 1, 1, I'm going to be stretching the y value by 2 because that's vertical. So instead of going like up 1, I would be going up 2, but of course I'm going down. So I'm going to count here. I'm going to go right 1 and down 2. Left 1 and down 2. You can also use your property of reflection right there. If you wanted to plot an additional point, remember your next point is at 2, 4. So you would be vertically stretching the 4. So that would mean if you count out right 2, you have to go down twice of 4, which would be 8. So if we're up at 2 already, we would have to go down 8. So I would count right 2 and then down 8. 1, 2, 3, 4, 5, 6, 7, 8. I'm going to point here, reflect it on the other side. And I've got a parabola that opens down. The one thing you want to be careful of with parabolas is don't treat it like absolute value where you keep going down 2 over 1, down 2 over 1, because parabolas don't have side slopes like absolute values. They're not lines. Okay. So it does look narrower than the parent graph, which it should because we vertically stretched it. It's opening down because it has a negative and it's been shifted left 3 and up 2. Let's talk about domain and range. So domain for a quadratic function is, again, x equals all real numbers. You can use your fancy R right there. You can square any number that you want. There are no rules against that. So we can put in any x's that we want and we'll be able to square it. Range is going to be restricted by your vertex, whether you have a max or min. In this case, our highest y value is the y coordinate of our vertex, which is 2, and everything below it. So we're going to say y's that are less than or equal to 2. And then the last thing we want to do is identify our increasing and our decreasing intervals. So remember, those are all going to be in relation to this axis of symmetry, which is at x equals -3. So on this side we have x less than -3. On this side we have x greater than -3. Okay, so we're breaking up the coordinate plane into 2 left and right sides, and then just decide what it's doing. Is it increasing or decreasing? So over here on the left side, if I read my graph from left to right, follow my blue ink, I am increasing. So my increasing is x less than -3. Once I hit my vertex or my turning point, I am decreasing. So for all x's greater than -3. Notice axis of symmetry, increasing and decreasing, all deal with h, the x coordinate of your vertex. Range should always deal with y, the y coordinate, k, the y coordinate of your vertex. Okay, I'll do one other example because I want to show you what to do if you have a vertical shrink instead of a vertical stretch. So we'll do another example here. This new g of x is going to be g of x equals 1/2 times the quantity x minus 1 squared minus 3. So start with my labeling. My vertex is 1, -3. My axis of symmetry is x equals 1. I'm going to go ahead and start my graph there. So I'm going right 1 and down 3 for my vertex. That's where my axis of symmetry is going to be. Now, I do know that my parabola is going to open up because I have a positive A in the very front, so the parabola should open up. And then I have a vertical shrink by 1/2. So think about your parent graph. You got the point 0, 0, okay, and then you have the point 1, 1. You're going to be vertically shrinking that point by 1/2. So that would mean if you go right 1, you should only go up 1/2. We can't use the same thing we did with absolute value, which is to go up 1 and over 2, because we don't have constant slope anymore. So if I'm at 1, -3, and I go right 1, I only go up 1/2. So I'm at like -2.5, and that's okay. If you want an additional point, remember what's the next point on that right side or that right arm of the parabola? It would be at 2, 4. So then you'd be vertically shrinking the 4 by 1/2. So that would mean if you went right 2, you should only go up 2, which is 1/2 of 4. So I'll go back to this point right here, my vertex at 1, -3, and I'm going to count right 2 and then up 2. So I'm at the point 3, -1. And then I can easily just kind of like reflect over the axis of symmetry and then draw my parabola. So it's important to remember that with the vertical shrinks on a parabola, you cannot do what we did with absolute value, which is count up 1 over 2. Okay, that doesn't work anymore because we don't have constant slope. All right, domain is going to be x equals all real numbers. Range is y's that are, sorry, that looks like an x, y's that are greater than or equal to -3. Remember that should match your k value in your vertex. And then for increasing and decreasing, okay, remember focus here is your axis of symmetry, x equals 1. There's 2 sides to that. X's that are less than 1 and x's that are greater than 1. And you just decide on that side, what's it doing? When x is less than 1, follow my red line, I'm decreasing. So I'll put x less than 1 there. Once I get to my turning point, turn around, and for all x is greater than 1, I'm increasing. That number in increasing and decreasing should always match your h coordinate of your vertex or your x coordinate of your vertex. Okay, so definitely stretches and shrinks are going to be something you'll want to practice on your homework. When I'm checking quizzes and tests, I'm going to be checking that you have at least one additional accurate point that you can reflect over on the other side. So really you have 3 accurate points, the vertex and then the next 2 points. Okay, last example. We can also use this vertex form in our transformations like we did in first chapter to change or write equations of quadratic functions. So let the graph of G be a vertical stretch by a factor of 2 and a reflection in the x-axis. Important here is that it's followed by a translation 3 units down. And this is all happening to the function f of x equals x squared. We're going to write the rule and identify the vertex for G. So anytime your book gives you this scenario where you're doing some transformations followed by another transformation, these are the examples where I always wrote an h of x first. So I'm going to use my function notation, and I'm going to work with the stuff in red. So my new h of x, what am I doing to the original function? If I vertically stretch it, I'm multiplying the y by 2. And if I reflect in the x-axis, I'm multiplying the y by negative. So really I'm doing two things to the y. I'm multiplying it by a negative 2. So a vertical stretch and a reflection in the x-axis can be negative 2 times f of x. And f of x is just this function, x squared. So h of x is negative 2 times x squared. And I'm done with h of x. If I want to get the g of x, now I've got to take this equation, my h of x, and do the translation 3 units down. So remember, for g of x, if you're translating one function 3 units down, you're just going to take h of x, the y value, and subtract 3. So I would do g of x equals negative 2x squared, that's what h of x is, subtract 3. And this would be my equation. It's important that you follow the order, because if you did minus 3 in the original one, you don't want to distribute the vertical stretch to that, so that comes later. And remember, if you're moving down, you're doing it to y, so you just put it on the end of the function. If we were moving right or left 3, we would have to put that inside with x, and we would protect it with a parentheses. Okay, so read those very carefully. Look back at your function notations from chapter 1 and see if you can write the equations. If you want to, you can always go online to Desmos and type in the original problem and your new equation and see if it looks like the transformations that have been described to you. All right, that's the last of my examples. So you have your gold sheet. Your homework is on the gold sheet there. You're working out these problems. And I do have graph paper. If you would like a piece of graph paper for the 4 or 5 problems that you're graphing, you can use that. Please work on your assignment during this time. I'll be coming around tomorrow to check your answers. Thank you.